So we just saw that there are quite a few similarities and differences between electrostatic force and gravitational force. One of that similarity is your superposition theorem. So we have understood superposition theorem that when we have a particular, say, object and another object, and we have a third object, the amount of pull, say this is because of gravity, the amount of pull because of one will not be affected by the absence or presence of 3, right? If this is 10 Newton, it doesn't matter if mass 3 is present or not, it will remain to be 10 Newton. And it is same when it comes to charge as well. So instead of mass, I can change this to charge. Just a second, it will take a second to, yeah. So this is say 2 and this is say 3 and this is say 1. The amount of charge or force with which charge 1 is pulling charge 2, it will not change because of presence or absence of Q3. Remember, net force is different, individual forces are different. Net force, of course, it depends on all the charges. So net force is what we are trying to figure out using superposition theorem. So the idea of superposition theorem is that if we have little bit of effort, the total effort, if we have to find, we have to make use of superposition theorem. That's what superposition theorem helps us in. So we can imagine bunch of kids, jumping around trampoline. So each kid has their own effect on trampoline. But as a whole, if they jump at the same time and all of that, the total effect with which the trampoline will go down will be superimposed or superposed. The total effect is sum of all of them. That's what superposition theorem talks about, right? You guys have seen all of this already. This is the official statement. The principle of superposition theorem states that the net electrical force on a given charge due to a system of charge is equal to, keyword over here, vector sum of the electrical force exerted on it by individual charge. Okay, we're looking at the vector sum. Let's look at it practically. Say this is your Q and say this is Q1 and Q2, or we can call this as Q1, Q2, Q3. And these charges are at this particular positions. Just a second. Again, this is not. These are your position vectors. Again, it's not working properly. Let me try it, guys. Just a second. Okay, now it worked. So these are your position vectors of the charges. So this is nothing but your R1, R3 and R2. And this is your displacement vector. Again, it's not working. Okay, let me just continue with this itself. I guess. So that's your okay, sorry, I kind of got distracted. So where were we? This is your displacement vector, vector, and that would be your R3, 1. Again, this representation can change. So here we are sticking to R, to and from. If they flip it, it's nothing, it's just a representation. So don't think too much about this. So the force will be in the direction of line connecting the centers, right? Sorry, my diagram is going to be bad because my pen is not working properly. F13, again, this is also to and from. And if all the charges are of same nature, then it will be a pushed force, right? That's your basic diagram. Now, all this force talks about is, all the superposition theorem, what it talks about is, let's first find the force on q1 by q2, which is given by f12, which is equal to k times of q1 q2 by r12 square in the direction of r12. That's it. Then by q3 is given by f13, which is equal to k times of q1 q3 by r13 square in the direction of r13. Now, as per superposition theorem, what do we have? We have f. Okay, just take a second. It came back. Again, it will take a second. Yeah, f total or f net actually. Again, I can't erase this, so I'm going to scratch it. f12 plus f13. That's all. Okay, so all we have to do is this. So this is basically equal to k times of q1, that is common, and everything else is q2 by r12 square into r12 plus q3 divided by r13 square, and the unit in the direction of r13, right? So in general, we have f net is equal to k times of whatever charges we are looking at, say q1. So this would be, I can write it in this manner, sum of, right, qi divided by r1i square r1i unit vector, where I will vary from 2 till n. So this is your general representation. So what is n? N is the number of charge, the last charge, where n is the last charge, where n is the last charge. Okay, so this is your unit vector form and all of that. So if I have to put it in the form of your position vectors, same expression or same, okay, it's not changing color, now it's changing color. In terms of position vector, what are we looking at? We have f net, right, on charge 1. We'll represent it with charge 1, makes it a lot more presentable, more information. So q1 by 4 pi epsilon naught, right, summation of 1 to n. So this will be qi divided by, what will change over here is, in place of r1i, all I'll do is r1 minus ri square, and this also we can represent as r1. Oh yeah, that would be, we have to divide it. So basically that would be your r1 minus ri. Okay, so this is your direction divided by the magnitude. So this will give us what? This will give us our unit vector. Okay, so let me make it very clear. This particular thing, this is our unit vector, which is given by a vector, say a, by its magnitude, right? That's what I have done over there. Okay, so this is your vector presentation. Quite simple, because r12 is nothing but r1 minus r2. Again, you have to be strong with vectors. Please see the basics before doing any of these chapters. Math has to be very strong. If not, you're not going to learn. Okay, so what is that we looked at? We started the chapter with understanding that we have charges. Charges exist in nature. We are made up of charges. Charges are flowing in us, right? That's how we are able to think and move and act and all of that. So these charges will exert force on other charges. It can be a push or a pull. How much push or a pull? It's given by your Coulomb's law. Then we saw that it's medium dependent and so on and so forth. It has its own detail, own maths. Now we're looking at what if we have more than two charges? How does this affect? Well, it is seen in nature that the charge on, say, a pull or a push on Q1 or Q2 is not going to be affected by Q3. But of course, the net charge will not be the same. The net charge, resulting charge will be, resulting force will be different. And that resulting force we can make use of superposition theorem to find out. So the statement is that you find the net electrical force by vectorially adding the individual electrical forces. So vector addition is something that you guys have to be very familiar with. Now we just took a very simple example wherein we had two charges affecting the third charge. So we're going to represent the position with position vector, and then we have our displacement vectors, right? So all of this representation we have done, and we know that the forces act in the line of the line connecting in the direction in the line of the line connecting Q1 and Q3. Okay, basically I am not able to state that. Basically it will be along this line and this force will be along this line. That's what it means. Officially I don't know how to state it, I forgot. It can be either pull or a push. Now when we know that this forces are of particular direction, we can add them vectorially to find the resultant, right? So first the funda is that, see, basically this is how we have to do numericals, what we are trying to figure out, the derivations and everything. Find the individual effect, right? Q1 getting affected by Q2 and Q3. Once we have that, use superposition theorem. That's the entire funda, So the entire thing is that you can find the net force on one by just adding F12 and F13. Right? In both of them, K and Q1 is common, so I took it out. So in general, if we have more than two charges, the pattern will change to this. Is it not? Right? And what if we want it in terms of position vector? Quite simple. All we have to do is, in place of R1I, I'm going to write R1 minus Ri. Like in place of R13, I can write it as R1 minus R3. And the unit vector, we can find it with the help of the magnitude divided by its, the vector divided by its magnitude. That's how you'll be able to figure out the unit vector. So this is basically a replacement for R. Just a second. This is our replacement for our R1I cap. Okay guys, so quite simple. But again, if you find this difficult, I can tell you, please pause this entire chapter, go back to vectors, learn that and come back.